This resource is the sixth in a six-part series on exponents and logarithms. Part 1 defines exponents and logarithms. The exponent laws are defined, and justification for the exponent law of multiplication is provided. We consider how to transform between exponent notation and logarithmic notation, and define two special bases for logarithms. Part 2 explores expanding and contracting logarithms. Multiple examples of each are provided. Part 3 demonstrates solving logarithmic equations, with examples provided. Part 4 considers solving exponential equations. A general solution method is provided, and examples are given. Part 5 delves into solving exponential growth equations, with examples. Part 6 looks at solving exponential decay equations, with special emphasis on half-life problems. Exponential decay models situations where a population continuously decreases by some percentage. It behaves exactly like exponential growth. In fact, it uses the same formula. A, the amount at the end, equals A sub 0, the initial amount, multiplied by e raised to the power of a constant k times t, the elapsed time. The only difference is that for growth, the constant is a positive number, while the constant is negative for decay. As with exponential growth, you may need to find the amount present after some given amount of elapsed time, or find the time that needs to elapse before some amount remains. Decay equations usually take this second format, as researchers are usually interested in some critical population sizes. For example, how long will it take for an animal population to drop to some level where it cannot remain viable and begin to go extinct? Let's look at an example. Suppose we consider a forest infested by gypsy moths. These pests target primarily oak trees, destroying the vegetation. The moths in their caterpillar form kill off 40% of the trees per year, in this example. The forest originally contained 15,000 trees. We want to find the amount of time before the forest only contains 15 trees. Because 40% of the trees die, 60% of the population remains. This 60% represents the ratio of the ending population to the initial population after 1 year. In other words, the 60% is the result when performing the first step in solving for the constant k, a division. We are left with 0.6 equals e raised to the k times 1. We take the natural logarithm of each side of the equation. Because natural logarithm and e raised to a power are inverse functions, they cancel each other out. We are left with the natural logarithm of 0.6 equal to k. Using a calculator, we find that k is approximately equal to negative 0.5108. Now that we know the constant k, we can plug in our information to find the time. Our target population is 15, and the initial population was 15,000. Entering this information into the formula, we have 15 equal to 15,000 multiplied by e raised to the negative 0.5108 times t power. Divide both sides of the equation by the initial population of 15,000. Take the natural logarithm of each side. Note that we calculated the 15 divided by 15,000 and got a result of 0.001. We could have left the division as a fraction, but the result was a nice decimal, so we chose to change to decimal notation. As always, natural logarithm cancels out the e. We have the natural logarithm of 0.001 equal to negative 0.5108 t. Divide both sides of the equation by the decimal amount. We find that t is equal to the natural logarithm of 0.001 divided by negative 0.5108. Using a calculator, This amount is approximately equal to 13.5 years. A special form of exponential decay is when the diminishing quantity is radioactive. Radioactive materials naturally undergo a process in which they transform into safer materials. Each radioactive material has an associated time called the half-life, which is the amount of time required for half the radioactive material to decay into a non-radioactive form. The constant K is simpler to find in half-life problems than other exponential decay problems. The constant for a half-life problem can always be found by dividing the natural logarithm of 0.5 by whatever is the half-life of the material. Let's look at an example. Strontium-90 is an isotope created in nuclear reactions with a half-life of 28 years. Suppose a nuclear incident happens that releases 60 grams of strontium-90 into the atmosphere. How long will it take for the strontium-90 to decay to a level of 10 grams? First, we need to find the constant K for this problem. We can use the formula because it is a half-life problem. Therefore, the constant K equals the natural logarithm of 0.5 divided by the half-life of strontium-90. Inserting the half-life, K equals the natural logarithm of 0.5 divided by 28. This amount is negative 0.02476 to 4 significant digits. We know the initial amount was 60 grams, and the target amount of strontium-90 we want to remain is 10 grams. We can plug this information into the general form for exponential decay, along with the constant K that we just found. Divide by the initial amount, 60, on both sides of the equation. Take the natural logarithm of both sides of the equation. For this problem, we leave the division as a fraction to maintain precision. The natural logarithm and the e cancel each other out, so we are left with the natural logarithm of 1/6 equal to negative 0.02476 times t. Divide by the decimal to solve for the elapsed time t. We use a calculator to find the natural logarithm of 1/6 divided by negative 0.02476. We find that it takes 72.37 years elapsed for a 60-gram sample of strontium-90 to decay to 10 grams of the radioactive isotope. Exponential decay models situations where an amount decreases by a consistent percentage. One example would be air pressure as elevation increases, as demonstrated by the picture of the plastic bottle being crushed demonstrates. Exponential decay equations have the same format as exponential growth. The only difference is that the constant for decay is negative. A special form of exponential decay involves half-life problems, which have a nice formula we use to find the constant K. When solving exponential growth or decay problems, remember that the general process is divide, take the natural logarithm, and divide. First divide the ending amount by the initial amount, then take the natural logarithm of that quotient. Finish by dividing the logarithm by number from the exponent of e. So while these application problems can appear really hard and confusing, the solution method is pretty straightforward. Hopefully your confidence in solving these problems will now grow exponentially.